Good afternoon. Can everybody hear me?
Yes.
Good. We will look at a group of questions that are probably best illustrated by the following algorithm. Suppose we have a function, f of x, and it tests whether x is equal to 0. And if that's the case, then it returns 1. Else, it returns 1 plus f of x minus 0.2. Now, I'm not in any way suggesting that this is a particularly interesting function. As far as the result is concerned, it really isn't. It is a fairly stupid function, but it is very, very simple, and it will allow us to look at things that are probably quite surprising. So if we assume that this is an algorithm, then this is, of course, perfectly feasible. And if we have a function called f of 1, then that obviously is going to go into the else branch. So we call f of 1, which is 1 plus f of 0.8. And then we call that again, and f of 0.8 is 1 plus f of 0.6, and f of 0.6 again is 1 plus f of 0.4, and f of 0.4 is 1 plus f of 0.2, and f of 0.2 is 1 plus f of 0, and 0 is 1. So effectively, we're going to return 1, 2, 3, 4, 5, 6. The algorithm clearly will provide us with the value 6 if we call f of 1.0. And that is entirely straightforward, and really I'm belaboring here something that is entirely obvious to you, I assume. You probably think that what is happening here is kind of boring, and it is until we actually start implementing that as a program. What if, now, of course, I've written it in a way that lends that function to be directly implemented as a program, as a program fragment. And so the question is then, what do you think is going to be the value that is returned if we call this with f of 1.0? Of course, you have already been accustomed to the various landmines I sprinkle all over the course, so none of you is going to tell me what you really think. But what would you expect this call to that function with parameter 1.0 to return? Nobody? Now we've already gone through the algorithm, and so the algorithm says it's going to be 6, and that is completely straightforward. So does anybody think that the function call to the program that implements this function should be any different? Well, I am limiting it to the question f of 1.0. Let's forget about everything else. Well, obviously there are other things. If I call that with something that, if I call it with 1.1 or with -10, then obviously there are many, many more problems with this code. But let's just look at f of 1.0. What is going to happen if I implement this function as it is written? Basically, it can be taken just as it is, and call f of 1.0. What's going to happen? Well, I guess all of you expect to get 6, don't you? And of course, by now you're all aware that I wouldn't be lecturing about these trivialities if that were really true. And in fact, what is going to happen in this particular case is that it will crash. And why will it crash? Because of a stack overflow. What is going to happen here? Well, what is going to happen is that in contrast to what we did in the algorithm, which is perfectly straightforward, and it's written down there, the crucial issue here is that point 2 does not have a finite binary representation. So the binary representation of point 2 is different from the decimal point 2 that we have. Because in binary you can't represent 0.2 finitely. Now, I'm sort of pleading to misleading you, because had I written 1 divided by 3, then you would all know perfectly well that that doesn't have a finite representation in decimal, and therefore also not 1 in binary. But point 2 has a finite representation in decimal, but it does not have a finite representation in binary. So what that means is, therefore, that you're going to approximate the value, decimal value 0.2, with a binary number that presumably is as close to the decimal value 0.2, but it isn't exactly 0.2. And so the fact that this is not exactly 0.2 means that we are definitely not going to be able to hit the x is equal to 0.0. And because we're not going to hit x is equal to 0.0, we're going to be off a little bit. It will continue, and it will continue, and will continue, because we'll never hit 0.0 exactly. And that will go on until we have exhausted the amount of space that was allocated for the stack. And so the result of calling f of 1.0 is going to be a crash. caused by the stack overflow. That is the result of the inability to hit the basis case x equal to 0. So that is, of course, not exactly what we expect, but we have only begun to explode the first of several landmines. So one may say, all right, well, we do accept that this is, these are floating point arithmetic. We all know that floating point arithmetic is a little bit more complicated than fixed point arithmetic. And so if we don't hit that 0.0, how about if we just make it less than or equal to 0.0? Now, in that case, we're not going to get a stack overflow. We are going to hit that condition. It will eventually, because this is going to be reducing by 0.2 every function call, we're guaranteed to get this condition satisfied, and so eventually we will return something, and that in fact is true now for every value as a parameter. 1.1, 2.33, minus 200, it will terminate. So we will not have any stack overflow anymore. However, we don't really know what is going to be the result. Now, if it is an algorithm, we know perfectly well, this is 6, and that's what we expect to get if we have f of 1.0. But that's not really necessarily true. You see, we've already established that the binary representation of 0.2 isn't exactly equal to the decimal representation. But there are really two possibilities. The binary representation of 0.2 could be less than the decimal 0.2, or it could be greater than. Either one of them is possible. And so, depending on what it is, we will actually, as you will see, I will work it out, get different responses to f of 1.0. Even with that modification x less than or equal to 0.0 as the basis case for the recursive function call. So let's take the first case, that the binary representation is less than the decimal representation. Well, in that case, instead of 0.8 here, we're going to get something that is a little bigger than 0.8. And then continuing, starting from something a little bigger than 0.8, we're now going to get something that is a little bigger than 0.6, and then a little bigger than 0.4, and then a little bigger of 0.2, and then a little bigger than 0.0, which means it doesn't meet this requirement yet, so we're going to have another call, and now this is going to be meeting that x less than or equal to 0, because this is greater than 0.0, so this is not true, and so we have another recursive function call, which means we get 1, 2, 3, 4, 5, 6, 7. If the binary representation of 0.2 is, in fact, a little smaller than the decimal. On the other hand, if the binary representation of 0.2 is a little bigger than 0.2 decimal, then we're going to get this original. We get something that is a little less than 0.8 here, and a little less than 0.6 here, and a little less than 0.4 here, and a little less than 0.2 here, and a little less than 0 here, which means it is now less than or equal to 0. And so we get 1, 2, 3, 4, 5, 6. Of course, none of you, I submit, has any idea whether the binary representation of 0.2 is less than decimal 0.2 or greater than decimal 0.2. So as a result, none of you really knows whether the value that is going to be returned is 7, which is if binary 0.2 is less than decimal 0.2, or 6, which is if binary 0.2 is greater than decimal 0.2. So this is of course a fundamental flaw of this, because now we really have no way of even looking at this code and mentally executing it and determining what is exactly the response. Is it 7? Is it 6? We don't know what the binary representation of 0.2 is with respect to decimal 0.2. And therefore, we have no basis to determine whether it's going to be 7 or 6 when we call f of 1.0. So that's the second problem. We have more problems with that. The fundamental problem that we haven't explored yet is, of course, that not only do we not know whether it's the first case or the second case, binary 0.2 less than decimal 0.2, or binary 0.2 greater than 0.2, it is actually quite possible that depending on what computational platform you execute that program, you're going to get different results. So how on earth can that be? Well, you may have a 32-bit arithmetic platform, and in 32 bits, 0.2 binary is less than decimal 0.2. You may have a 64-bit arithmetic platform, in which case binary 0.2 may be greater than decimal 0.2. There is nothing that actually tells you that this will always be the same, whether you have 16-bit arithmetic or 32-bit arithmetic or 64-bit arithmetic. It is quite possible that in one of these three cases, the value is less than in another one of those three cases. It is greater than, because essentially what will happen is that the actual representation is determined by whatever is closest to the real decimal 0.2. And if you have 32-bit arithmetic, it may be a value that is less than 0.2 decimal. And in 64-bit arithmetic, it may be something that is greater than decimal 0.2. And you really have no idea to predict that unless you actually go exactly into the computer arithmetic and determine it very, very, very carefully. So that is the third problem, that your program is not portable. Now, we've already seen cases where that is the case last time when we talked about lazy evaluation. Portability goes out of the window. Well, this is another instance where portability can go out of the window. In this case, not because of the compiler, but because of the internal representation, 64-bit, 32-bit, whatever. It is exactly the same program, but the actual value of 0.2, which of course isn't decimal 0.2, it is binary 0.2, depends on the number of bits that you have available. And so as a result, you can very easily get a situation where you run this program, now even with the modification x less than or equal to 0.0, which guarantees that it will always terminate, but you will get you may well get a value on one computer, and you get a different value on another computer, even though it is exactly the same code. So what that really means is that 0.2 is not a constant. And does not have the value 0.2. So that is, of course, perhaps a little surprising, certainly a little troublesome, because this is the kind of thing that flies in the face of what it is that we expect when we write a program that presumably is portable. Well, in this case, it isn't. So what is the upshot of that? Well, the upshot of that is that this should never be coded. Whenever you deal with this type of algorithm, and as an algorithm it is perfectly acceptable, but whenever you deal with this type of algorithm, it has to be transformed into a different program. In this case, I would simply go to integers and multiply everything by 10, in which case I'd still test for 0. Now, not 0.0, but for 0. And then I return 1 plus f of x minus 2, not 2.0, but 2. And so everything then is done in terms of integers. And so in this case, we then obviously avoid these pitfalls. But it is important that you understand that there is a vast chasm between a program and the algorithm on which it is based. For the algorithm, we could easily just have testing for equality, and there's no problem. If we do that, then of course the program is going to crash miserably. And even if we fix it, then yes, we forced it to terminate, but we are not at all certain what the actual value is going to be. In this particular case, for f of 1.0, it could be 7, it could be 6. And for all practical purposes, we have no way of determining what the outcome is going to be. Now, what this means is, of course, that we have here a number of weird situations. We may, for instance, look at something like a sum. this is very similar to the logarithm. So we go 1 to n, and let's just call this f of n. Now, mathematically, it is obvious that f of n is always strictly less than f of n plus 1 for all n greater or equal to 1. So any n, f of n is going to be less than f of n plus 1 because obviously they differ. F of n differs from f of n plus 1 by 1 divided by n plus 1. That's mathematically. Computationally, there always exists an n sub 0, a minimal n sub 0, such that f of n sub 0 is going to be f of n sub 0 plus 1. So in other words, at some point this summation basically stops. Doesn't do anything else. Nothing changes, and therefore obviously if we add another term, it's still going to be the same. And so that means that we really have here a situation that is somewhat counterintuitive. Well, it has to do with the fact that there exists a max epsilon which is largest, such that 1.0 plus max epsilon is equal to 1.0. Why? Well, you have to go into arithmetic, computer arithmetic. So typically you have a mantissa, and you have an exponent. And depending how nitpicking you are about the computer arithmetic representation, I'm sort of simplifying things. I'm assuming that the mantissa is sort of what you expect it to be, which of course it usually isn't in the internal representation. The mantissa is basically assumed to be a number that is 0.1 and then other stuff, and the exponent then is whatever. So if you want to represent 1, then you have 0.1000, and you have 1 here, because that basically says exponent 1 means you put the 1 before the decimal point. Now, of course, if you actually want to look at the true internal representation, well, obviously the decimal point is not going to be stored, and neither is the 1, because with the exception of 0, which is represented slightly differently, everything starts with a 1 after the decimal point, because the exponent can be normalized so that that's the way it is. And so because when you deal with computer arithmetic, people are doing all kinds of tricks. Essentially, neither the decimal point, or actually the binary point in this case, this is binary, of course, nor the one after the binary point are going to be represented. So really what is going to be stored in the mantissa is whatever follows that one. And so if you have 4 bits in this case, then 0, 0, 0, 0, 1 is going to be the binary representation of 1.0, because it's basically this 0.100000 and with the exponent 1. And so anyway, let's not tie ourselves into knots. Let's just let's assume we have 4 bits, and that means we're basically writing 1000. These are the 4 bits that we have. And if I now add to that something that is 00001, then obviously I have this, and because I have only 4 bits, that 1 disappears, and I basically get back 1000. And so this would be a value that, when added to this value, is going to give me that value back, even though it is obviously positive. And so this is not necessarily the maximum of all those, but there obviously is going to be a max epsilon that has the property that, when added to 1.0, is going to give me back 1.0. And so that's, of course, what is happening when I look at this summation. 1 plus 1/2 plus 1/3 plus 1/4 and so on, because eventually the f of n sub 0, so I have 1 plus etc. 1 plus n sub 0, this quantity is such that when I add the next term, 1 divided by n sub 0 plus 1, this essentially will be a scaled max epsilon. It's scaled because this sort of assumes the role of the 1.0. So this is obviously bigger than 1.0. And so this is also going to be bigger. And so if we scale this down to 1, and scale this also by the same factor down to whatever it becomes, then that takes the role of the max epsilon. And when this happens, I basically have an instance of a scaled instance of that. Now, that, of course, is not the kind of thing we would like to see, because, well, we know mathematically that f of n is always less than of f of n plus 1 for any n. So the fact that computationally that is violated is troublesome, to say the least. It gets worse. At this point, I've basically implicitly assumed we're going from 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on, adding up from left to right. There's nothing that says I have to do that. I could go backwards. So if I want to get f of n, instead of going 1 plus 1/2 plus 1/3 plus 1/4 and so on, I'm going to do 1 divided by n plus 1 divided by n minus 1 plus 1 divided by n minus 2, etc. 1 6 plus 1 fifth plus 1 fourth plus 1 third plus 1 half plus 1. What is going to happen is that, yes, we're going to have a similar situation. There exists another n0 prime such that f n0 prime is equal to f n0 prime plus 1. And let me do arrow, backwards arrow on top of the f to denote that I'm going to go from the smallest term towards the largest term. But it turns out that that n0 prime is going to be significantly larger than the n sub 0. So depending on in what order I am going to add up, whether I'm going to add up from left to right, which is the sort of natural way of doing things, or from right to left, which is sort of the weird backwards way of doing things, I'm going to get different values. So if I take that f of n sub 0 plus 1, which of course in the left to right addition is going to be equal to f of n sub 0, well, that's going to be different in the f backwards of n0, not the n0 prime, but that n0 plus 1 is still going to be bigger than the f backwards of n0. So depending on how we are evaluating the sum, we may get rather different results. That is a fairly unpleasant situation, which of course is ultimately due to the fact that we have that max ips that is always present when we deal with floating point arithmetic. So in order to get a bit of an idea what is happening here, let's be a little bit more systematic. And let's look at the standard mathematical properties. Mathematical identities. We have commutativity. We have associativity. And we have distributivity. And we have both addition and multiplication. So commutative means a plus b is b plus a, and a times b is b times a. And associative is a plus b plus c is a plus b plus c. And the same thing for multiplication. A times b times c is a times b times c. And finally, distributivity would be a plus b times c is a times c plus b times c. And looking at that, we now can differentiate between two different systems. We have floating point and we have fixed point. And so turns out that for both floating point and fixed point, in addition and in multiplication, those identities hold. So a plus b is b plus a, and a times b is b times a in both floating point arithmetic and fixed point arithmetic. And so that is somewhat comforting. What is not comforting is that that's the end of that. It doesn't hold for associativity, and it doesn't hold for distributivity. Not only does it not hold for floating point, it also doesn't hold for fixed point, which of course is probably a little surprising, because you've over the years probably have been led to believe that floating point is sort of evil and dangerous and stay away, but fixed point is safe and nothing bad can happen. And so I'm going to show you that lots of bad things can happen. Well, associativity. A plus B plus C is A plus B plus C. That's the identity, the mathematical identity that we fully expect to hold, and of course it doesn't. For instance, we can take A is equal to 1, and B and C are equal to max epsilon. So what does that mean? We have A plus B, which is 1 plus max epsilon, and 1 plus max epsilon is 1. And so A plus B is 1, plus C, which is max epsilon, is 1. So here we have 1 on the left-hand side. And now we look at the right-hand side. B plus C is twice max epsilon. By definition, this max epsilon is the largest value such that 1 plus that value is equal to 1. So if I take something that is bigger than max epsilon, then I'm going to get something that is bigger than 1. And therefore, what I'm going to get here is something that is bigger than 1. And so I have then, if this mathematical identity were to hold, I would now have a statement that 1 is equal to something that we've established is bigger than 1. That obviously is false. Now, what about fixed point? Well, if you have any finite representation that's really not tied to fixed point, but it is more obvious for fixed point, you essentially have a value that is the largest representable value. I'm squirming here a little bit, because if you are very careful about your representation of numbers, you probably know that there are some representations in which things are not symmetric about 0. We tend to think that, well, if we have a number that is positive, then we can get the same number but with a negative sign. That's sort of a tempting assumption. It's not really quite true. There are some representations where the number of positive numbers, fixed point numbers, is off by 1, from the number of negative numbers. Usually you have one more positive number than you have negative numbers, which means that you can't just put a minus sign in front of the positive number and get a representable integer again. But if you want to be nitpicking and keep that in mind, you just don't take the maximum. You take something that is almost the maximum, but not exactly. If you ignore that nitpicking thing, then you can just say A and B are maximal, and C is minus B. So, as I said, if you want to be nitpicking about the arithmetic, then you have to do almost maximal rather than maximal, because in some cases you may not have C representable as minus B. So B would have to be one less than the maximum, but that's not really that important for the argument. So what is going to happen here? Well, if we look at the left-hand side of this supposed identity, we have A plus B. Both of them are maximal, or sort of maximal, but whatever we picked, maximal or sort of maximal, A plus B is not representable. This is going to throw an exception. It is an overflow. We can't represent A plus B. And once we have an exception for A plus B, then obviously whatever else happens in the computation, particularly this plus C, is immaterial. An exception plus something is going to be still an exception. And therefore, the left-hand side of the supposed identity is an exception. Now let's look at the right-hand side. We first have to do B plus C. Well, if B is equal to minus C, or C is minus B, then B plus C is 0. And so on the right-hand side of this supposed identity, we have A plus 0, which is A. So on the left-hand side, there's an exception. On the right-hand side, we have a perfectly good representable number, A. And obviously, that exception can't be equal to A. They're different, and therefore this is not an identity. This is different. So for fixed point, not happening. For addition, and we can do similar things for multiplication, we can, in fact, well, we can do the same the argument that we did for fixed point numbers, we can also do for floating point numbers. Again, in floating point numbers, you can have a maximal number. If you look at that representation, you have a mantissa and you have an exponent. Well, you take the mantissa consisting only of ones and the exponent consisting only of ones. That is obviously the largest number that you can represent. And so you can certainly do a maximum A and a maximum B. And when you add the two of them up, that will give you an overflow. And then if C is minus B, then you have the same situation here. A plus B is an exception, even if it were floating. I mean, this is now for the floating point representation. And in that case, we have A plus B is an exception, and therefore the left-hand side of this supposed identity for floating point is an exception. The right-hand side, on the other hand, is b plus c, which is 0, and a is that largest number possible. So we have here a perfectly serviceable number on the right-hand side and an exception on the left-hand side, which of course is not an identity. In fact, they're very different. We have a similar situation for multiplication. This is actually even simpler. We do a and let's just start with the fixed first. A and b are maximal. In this case, we can do maximal, and c is 0. So what are we going to get? We get a times b. If a and b are maximal, then a times b is obviously not something that can be represented. So this is going to give us an overflow. This is going to throw an exception, and therefore we have an exception when we evaluate this expression, and whatever we multiply afterwards, who cares? This is an exception on the left-hand side. On the right-hand side, well, we start with b times c. b times c is 0. So we have a times 0, which is 0. So we have an exception is equal to 0. Obviously not true, is not an identity. And so we have a counterexample for fixed point, which also works for floating point with exactly the same values. You can pick other values in floating point. You can get an analog of this max ips that is somewhat similar to for multiplication, but we don't really need to go into that. We have the fixed point, which can be done exactly the same way with different numbers, but floating point numbers, but same way with to give you a counterexample. And so what that means is that obviously we are looking here at this is not true, this is not true, this is not true, none of them are true. So this is clearly not an identity. And finally, distributive. We can do exactly the same thing. A and b maximal, and c is equal to 0. That will immediately give us the same situation because we get an exception, a plus b, and that gives us an exception. So whatever else happens, forget it. And then a times c is 8 times 0, which is 0. B times 0 is 0. So we have on the right-hand side 0, and on the left-hand side an exception. If you want a different example, well, you can have a and b maximal, and c is equal to 1 divided by b. For floating point, you can't do that for fixed because 1 divided by b doesn't have a fixed point representation. But if you do that, well, a plus b is going to give you an exception, so you're going to have a problem here. And you're going to get an exception here. And then over here you have a times c, which is a, b of course is the same as c. B is the same as a, so a times c is 1, and b times c is 1. And so here we have 2, and here we have an exception. And so that means that, well, the exception is obviously not 2. So that means that we clearly have here, yet again, a discrepancy between the two sides, the left-hand side throwing an exception, the right-hand side, giving us, in this particular case, 2, or in this case, 0. So in both cases, there are clear counterexamples to the supposed identity, which, of course, is a problem because we expect that our numbers, the numbers that we use in our programs, conform to the behavior that we expect from mathematical numbers. Those mathematical identities are identities that we expect to be true, and now we know that that is not the case. So the question then is, how serious is that? Well, you may argue, I have never run into this problem, and therefore I'm not really going to be terribly concerned. And that may not be an inappropriate attitude, but you should be aware that there are certain problems. And of course, the function that we talked about at the beginning clearly is a problem that is not a ridiculously unusual problem. So why do we typically have not that many problems with the fact that these mathematical identities don't hold? Well, now this doesn't really work for the function, but if you look at this situation, these are the numbers that you can represent. And that doesn't make much difference whether these are fixed point or floating point representation. In both cases, floating point, you have a smallest number and a largest number, and they're sort of almost symmetric with respect to 0. And the same thing for fixed point, depending on the arithmetic that you're using. It is a useful artifact to assume that they're also symmetric about 0 for fixed point. And so typically, if you look at these examples, they're sort of at the extremes where things go haywire. Most of the time when you do your work with the numbers that you're using are probably fairly close to the middle of that range, which is around 0. So you're not really going to work with those extreme cases where things can go fairly nastily wrong. And therefore, you're probably not going to run too many times into problems. Although, as I said, the function here that I illustrated at the beginning of today's lecture clearly is something that is well in the middle here. But that's, again, that depends primarily on the floating point numbers. I suppose that what surprised most of you was that these mathematical identities don't even hold for fixed point numbers. And there you are actually going to have to use sort of the extremes where things get rather strange, out of whack. And in that case, you're going to have to be concerned with those extreme cases. So Are there any questions about this? No questions? I assume by now you have gotten your assignment 2 grades. Is that correct? Okay, but grades have been sent out to. Okay, all right. Okay, I just wanted to make sure that somehow there was a miscommunication. You were supposed to get them at the same time as the other section, but that didn't happen. So now you have them. As far as the final exam is concerned, I believe your exam is going to be on the 4th of May, and the exam basically will be administered exactly the same way as exam 2 and assignment 2. I do want to emphasize one thing, though. If you did not, when you submit something to the email address 3320 at cs.uh.edu, you are supposed to get a confirmation. If you didn't get a confirmation within a minute or two, you probably should resubmit whatever you have, because in that case, it means we didn't get it. And we've been somewhat lenient for the exam too, but for the final, that's not going to happen. So make sure that you do get a confirmation, and if you don't, resubmit within 5 minutes. Any questions? Sure. The, for matrix multiplication? Right. Right. Well, obviously, if you want to use the algorithm, then essentially you're assuming that you can divide n by 2 in order to come up with that. So say you have n is equal to 45 times 256. So that's essentially 10,000. So n is about 10,000. So that means you have 45 times 256, and then you go to n is 45 times 128, and then you recursively go from there to 45 times 64, and then you recursively go to 45 times 32, and then recursively to 45 times 16, and then from there recursively to 45 times 8, then from there recursively 45 times 4, then recursively 45 times 2, and then you get down to 45, and at that point you're going to do the original 3 nested loops. Okay? Any other questions?
Yes, Professor. Where
Yes,
in
yes.
the book is this?
Where is what in the book?
I'm
What
sorry.
we did
The
today?
Yes, what we just did today. I just want to go over it one more time.
Okay, the function is in section 712. This is page 169 through 170, and the mathematical property, well, yeah, mathematical properties is section 8.3, which is pages 183, and then there's convergence through 186. Uh, that's basically the summation that I talked about. So, in essence, this is really, we talked a little bit about testing for equality. So all that is essentially chapter 8, but the meat of chapter 8 is basically 8.3, which is just 2 pages.
All right. Thank you.
Any other questions?
Oh, wait, I have another question, Professor. Do we have class next week?
You have class on Monday. That's the last lecture. So, and we are trying to return the grades to exam 2 by Monday. So I hope it will work. We're working on that. Any other questions? Uh, I